Okay, so welcome back student. So in last class we learned a very important concept of matrix, which is the diagonalization of that. So today I decided to do few other things, few identity of the matrix and few other small calculation to know. So let us start with a very simple thing. If a matrix, this is quite simple, but still I believe this. This is the eigenvalue equation. From this eigenvalue equation we can have many information. For example, if I operate A both the side, then it will be lambda square A, lambda square x, and this is nothing but A square. So it readily shows you a very important outcome, that A square, if A is A matrix has a eigenvalue lambda, then A square is the eigenvalue lambda square, and so on. So you can readily, with this very simple structure, you can find what is the value of A square, what is the eigenvalue of A square, and these things. Fine. Another simple thing, quick and simple, same equation I am writing, and for this equation if I operate say A inverse over x, then I have lambda A inverse over x. A inverse A is 1. So I can write this equation in slightly different way. Like this. So if I know what is the eigenvalue of A matrix with this, I can also know what is the eigenvalue of A inverse, which is just 1 by lambda. With this simple calculation also you can find it out. This is the 2 point I wanted to mention in the last class, but anyway, so you should remember these things. Now one important concept I like to introduce, or important, it is Hermitian matrix. It is Hermitian matrix. What is Hermitian matrix? A matrix H, if it is equal to H dagger, then this matrix is called the Hermitian matrix. H is equal to H dagger. So what is H, by the way, let me write it. So component wise it is H11, H12, H1n, H21, H2n, Hn1, Hnn. This is my given matrix H. What is H dagger? I know what is the dagger matrix. Dagger matrix is transpose followed by the complex conjugate. So I need to first transpose this matrix and then make a complex conjugate. So if I do that, then I will find H11 star, this H12 star, H13 star, everything will be star, H1n star, H21 star, H22 star, H2n star, Hn1 star, Hnn star. So the structure of the Hermitian matrix is this. Now the general element of H is Ij, and the general element of the Hermitian matrix is I mean in terms of H it is Ji, right, because if I is here, I make a transpose, so when I make a transpose, J will be replaced by I will be replaced by J, and with these things, and my condition is that H is equal to H dagger, so Hij has to be equal to H these things. If this is true, what happened when I put II both the cases? Hii is equal to H star II. II is nothing but the diagonal elements, and my Hermitian condition suggests that diagonal element both the cases is same as the complex conjugate. This is the same thing which is complex conjugate. So we know that if the same thing and his complex conjugate are same, this is a quantity whose complex conjugate is the same as the that quantity, then it has to be real. So Hii has to be real. So that means in Hermitian matrix the diagonal element has to be the real quantity. That is one important outcome that we find. Now the next most important thing for Hermitian matrix, why it is so important, you can readily understand that. Let me write down first the eigenvalue of the Hermitian matrix is real. So let me first explain very briefly why it is important in the context of quantum mechanics, because in quantum mechanics when we use some operator, this operator in matrix notation used by some matrix, when this operator, for example this is my operator say O, I operate over that psi, this is a state. If this psi is the eigenstate, I am getting some eigenvalue lambda and the state back. This is the same structural notation or the same structure that we are using in the linear vector space in the context of matrix operation. So now if this operator is a real operator, so the corresponding eigenvalue has to be real. So that is why in quantum mechanics we choose the operator which is Hermitian in nature. If it is Hermitian, then I always get the real eigenvalue. However, I did not prove that so far. So let me try to prove that. So let us see how one can prove that. So Hx, say this is the eigenvalue equation. If I make a dual conjugation of that, I need to write it like this. I have one equation this, I have another equation this, these two equations in my hand. So x from the first equation, if I do, I can have this equation from here to here. Using this equation, however, we have x h dagger, this is this quantity, but h and h dagger are same thing. So eventually, since h is equal to h dagger, I have lambda x these things is equal to lambda star this quantity. Fine. What is this quantity? X, the vector inner product with the same vector. So, this is a norm. So, I can write this equation like this. So, this equation suggests either this quantity is 0 or this quantity is 0, either this quantity is 0 or this quantity is 0. Now, this is a norm. So, we know that from our knowledge, we know that this quantity will always greater than equal to 0 and is 0 if and only if the vector is a null vector. So, that means for any arbitrary vector which is not a null vector, I will have a general equation where lambda is equal to lambda star. So, from this logic, I can say that lambda must be equal to lambda star. Lambda equal to lambda star is nothing but lambda is equal to real. A quantity which is equal to the complex quantity is only possible when the complex part, when the imaginary part is 0, and here lambda is equal to lambda star, that eventually means lambda is equal to a real quantity. Okay. So, now very briefly, I mean we need to show some example very briefly. So, say H a matrix 2 1 I minus I. Is this matrix a Hermitian? First we need to check it. So, when I make a H dagger, then the complex conjugate the diagonal element is real. So, no problem with that. That is one condition to form a Hermitian matrix, and this quantity should be the complex conjugate to each other. That is another quantity, another property of Hermitian matrix that is need to be followed. So, here we find that it is really followed. So, this if I rotate, then I will have the same matrix. So, this is nothing but H. Once I have that, then I can find out what is the eigen values of that, really the eigen values are real or not. So, let find the eigen values. So, characteristic equation or secular equation is this. Sorry, 1 minus lambda. This is my equation. So, 2 minus lambda, 1 minus lambda minus 1 is equal to 0. I minus I it is 1. So, there will be minus 1 because it is a cross multiplication. So, this characteristics equation, from that characteristic equation, this is a quadratic equation of lambda. So, I can find out what is the value of lambda. It should be real. So, let us check, just cross verify whatever the theory is given is. So, minus 2 lambda, then minus lambda, then plus lambda square, then minus 1 is equal to 0. Explicitly I am writing that. So, lambda square minus 3 lambda and then plus 1 is equal to 0. So, this gives me, let me once again check everything is correct or not. My Hermitian matrix is this. Try to find out what is the value of lambda. This is my characteristic equation, 2 minus lambda, I minus I, 1 minus lambda. So, determinant of these things 2 minus lambda multiplied by 1 minus lambda and then minus this 2 multiplication, I have this is equal to 0. Then I simplify. So, it is 2 minus 3x plus lambda square minus 1. So, this minus 1 gives me 1. So, I will get this. So, my lambda will be minus b plus minus root over of b square, which is 9, minus 4ac, which is 4 by 2a 2. So, finally, I will have 3 plus minus root over of 5 divided by 2, or 3 by 2 plus minus root over of 5 by 2, whatever. But the thing is that this quantity is real. So, just a simple check that any arbitrary Hermitian matrix I take, and after taking any arbitrary Hermitian matrix, I try to find out what is the value of his what is the eigenvalue, and when I find the eigenvalue, it comes out to be the real as expected. You can do the same thing for different other Hermitian matrices, and you can check by yourself that whether every time this is an exercise, you can take this an exercise, that every time you are getting the eigenvectors, eigenvalues which are real or not. Okay, so we have now a very brief idea about what is Hermitian matrix. Next few things, Hermitian, say A is a Hermitian matrix, and B is a similarity transformation like this. This is a similarity transformation with the fact that A is unitary matrix. So, A dragger is equal to 1. So, what I am trying to find out, that I have a matrix which is Hermitian. Now, I want to transform this Hermitian matrix in another coordinate system or another basis, where by making a unitary transformation, because this unitary transformation, if you remember, then the unitary transformation is required when I transform from a orthogonal basis, a set of orthogonal basis, to another basis which is still orthogonal to each other. If this is the case, then try to find out what is the value. Is this B is still Hermitian? A is Hermitian, I know. Is this a Hermitian? So, here I can write S dragger is equal to S inverse, the extra property that I have because of this unitary property. S is a unitary matrix. So, B dragger is S inverse A S whole dragger. Now, I know that if two multiplication are diagonal like this, so it is something like A B whole dragger is B dagger A dagger. Or ABC whole dragger is C dragger B dragger A dragger. If I do that, then it will be S dragger A dragger and this S inverse whole dragger. Now, S inverse is already dragger. So, it is S dragger I can replace to inverse. A dragger is A I already know. S inverse is S dragger. So, this is S dragger dragger. So, finally, I have S inverse A S. This thing is nothing but B. because this is B. So, that means B dagger is equal to B. So, what is the meaning of that? The meaning is if I have a Hermitian matrix in one coordinate system under one basis, I make a basis transformation. When I make a basis transformation, my new basis is also orthogonal or orthonormal to each other. In order to ensure the orthonormal transformation, I have a matrix, I have a transformation matrix which is unitary in nature. So, S dagger is equal to 1. So, under unitary transformation, so the conclusion is under unitary transformation, Hermitian under unitary transformation, Hermitian matrix remains Hermitian matrix. So, you make a unitary transformation, a Hermitian matrix is given to you. After making a unitary transformation, you have a new matrix, say B. So, B is also Hermitian. That is the conclusion in this entire these things. Okay. So, this is a small thing I wanted to mention, that what is the property. Apart from that, there are few under similarity transformation. I have few other properties. For example, A and B are related by the similarity transformation. So, A is a matrix given, B is given by S inverse A S. Now, need to find out what is the trace of these things. So, I know trace of AB is equal to trace of BA. So, here trace of A is this. After I have a matrix A whose trace is given by this, I make a similarity transformation with this and try to find out what is the trace of B. So, my goal is to find out what is the trace of matrix B. So, if I do that trace operation over B, then I need to do the trace operation both the side. I write it like this. This is nothing but unit. So, trace A. So, trace of B become trace A. So, that means what is the conclusion with this small thing, that under similarity transformation, trace of the matrix conserves. Trace of the matrix conserved. So, the conclusion is under similarity transformation, trace of the matrix conserves. Okay. Next thing is again a very short thing, that is A matrix is given, the corresponding similarity transformation is this. What about the eigenvalue or eigenvector of B? So, A has eigenvector like x with eigenvalue lambda. Suppose if this is the case, then what will be the eigen value of B? So, B, if I operate over x, I am operating A let me do in that way, try to. So, A is here, S is related to that. So, I write these things in this way: S inverse A x is lambda S inverse x, these things. Now, what I do, that S inverse A here in this place I put one S inverse. I can do that because S inverse is unity, this is unity. So, lambda S inverse will remain this quantity. I can now write S inverse A S inverse x lambda S inverse x. This quantity S inverse A S is nothing but B, because B is related to this. So, B S inverse x is equal to lambda S inverse x. S inverse x is also another matrix, another vector. So, if I say S inverse x is y, then B y is lambda y. This is nothing but a eigenvalue equation. Eigenvalue x is lambda, but eigenvectors are different. So, what is the meaning of that? I have a vector, I have A in my hand, lambda is the eigenvalue of A, x is the eigenvector of that. I make a similarity transformation and try to find out if B is my new matrix under similarity transformation, what is the value, what is the eigenvalue of that? I find the eigenvalue will remain same, that of A, but the eigenvector is changed, and eigenvector will be something like this. This is again a small thing. With that, I like to conclude this class, because in the next thing will be a very important topic, which is rank of a matrix, but I do not have that much time to explain that in this class. So, in the next class we will start a very important concept of rank of a matrix, and also like to learn what is the meaning of Cayley-Hamilton theory, and how using Cayley-Hamilton theory I can find the inverse of this. Is another way to find inverse, and also physical meaning of rank, which is also very important in terms of physics. So, with that let me conclude my class here. So, see you in the next class, where we try to cover rank of a matrix, and another thing is the Cayley-Hamilton theory, if time permits. Okay. So, see you in the next class.